Okay, welcome back, everyone. Let's get started. Today we have two topics that are related but also different. We will first cover some practical natural language processing, first like some statistical analysis of text, and then how can we use statistical learning, aka machine learning and classification for sentiment analysis. This is just going to be a primer. We don't really have time in this class to cover NLP extensively, but there are dedicated courses on NLP that I can definitely recommend. And the second part will also be related to text, but a little bit different, more from like a data cleanup, data wrangling perspective. We'll be covering regular expressions, which are these kind of like mini language to match substrings of a larger string. Before I get started, just a reminder, I have still a few of you still haven't registered your projects, but registering the project is absolutely necessary for us to set up the project groups in Canvas so that you can submit your work. So if you haven't done it already, please get back to me. Like you should know already, I've contacted you, but if you haven't, please get in touch. There will be an exercise today. And yeah, any other administrative questions? Remember that the project proposal is due. If you add a member, yes, please resubmit the project form, but also please send me an email so that I can kind of like keep track of that. Any other questions? Remember, there's like project proposals are due on this weekend. I forget which date exactly. These are important, and just make sure that they're on time. There's no late days for them. It's due Friday. Great, thank you. There's no late days for them, I think. And yeah, just one submission per group. Any questions of an administrative kind? Started. So we had the great guest lecture by Vivek Srikumar. He introduced the challenges of NLP and kind of like where the research frontier is currently. Just like a quick recap, historically, these were kind of rule-based systems, but NLP really took off when we took data-based, statistical learning approaches based on large data sets. When we took that to it, NLP really like improved a lot. And so like when I was a student, even a PhD student, NLP systems were not very good. They were pretty clunky. And nowadays we can talk to our Alexas or Siris and so on, and they will understand most of what we say. So there's been tremendous improvements. And there are, like he also gave, Vivek gave several examples of tasks in NLP, things like part of speech tagging, information extraction, sentiment analysis, like determining the attitude of a text, is it positive or negative, or semantic parsing when we try to translate natural language into some formal meaning representations. And one of the takeaways from his talk is that current state of the art for many NLP tasks is to find a good way to represent the text and then use machine learning or statistics tools such as classification or clustering. And so we will use NLTK plus scikit-learn to do some basic NLP tasks. And NLTK is this software library in Python, the natural language toolkit that allows you to do like things very easily with natural language processing. It also comes with like a library of texts which we can use. I should just say, like, if you like want to do some larger scale or more complicated NLP, there are alternatives now. There's like the Spacey library that you could consider if you're planning to use NLP in your project. Okay, so first thing is we will import the NLTK dataset, and then we'll download all of their text corpora. This might take a minute if you haven't done this already. It took me about like 10 minutes, but I already downloaded this. And then some imports, and yeah. So let's start with the basics of NLTK. So first thing is we will import. NLTK comes with a couple of books from Project Gutenberg, which are free. Like their copyright has expired, and so we have things like Moby Dick by Herman Melville, the Book of Genesis, like a corpus of chats, the script for Monty Python and the Holy Grail, some kind of like text from the Wall Street Journal, and then some email, and so on. And so we can work with these to just like look at some text. And so here I have imported all of these books, and they're listed as text 1 to text 9. And then I can simply, that these are just arrays of words. And so I can say, here are the 21st words of Moby Dick. And so we see here we have the title and then some information about the book. We can do some statistics about the text by like just looking at the text of the array, right? So we can see which one is longer. Is it Moby Dick or is it Monty Python and the Holy Grail? And we can see that Moby Dick is longer, but only by 10,000 words. We can check the frequency of a word by simply saying, like, by using the count function here on this book. And so here we are counting how often swallow was mentioned in Monty Python. And we like, one thing that you might wonder is like, well, what's the point of a swallow in this book or in this script? And you can do this by looking at concordance. And the idea here is like understanding a word often depends on the context. And you can, like John first said, you shall know a word by the company it keeps. And so if we run the concordance on swallow, we can get all of these sentences nicely formatted that contain swallow. So the swallow may fly south, a swallow carrying a coconut, a swallow needs to beat its wings, African swallow, European swallow, then a swallow's flight away, unladen swallow, European swallow, and so on. So we can see that there are a few different contexts in which swallow was used in this script. So similarly, if we look for the word Ishmael in Moby Dick, we can see like this is like how the book starts, call me Ishmael. And then similarly, we see that I, Ishmael here happens very frequently, I, Ishmael. So we can kind of conclude that Ishmael is maybe the narrator based on this simple analysis. We can also see which other words frequently appear in the same context by using the similar function. So swallow is similar to plover. And then if we say African, we have similar unladen. So that's kind of like the case, because here we sometimes have African swallow and sometimes we have unladen swallow, right? So for this text, those two words appear in a similar context. And if I have coconut, then I can see that there are all of these words that are used in a similar context. So if we want to see like these common contexts of two words, we can actually ask this in a particular, like with this particular function here. And we see that African and unladen have the common context swallow. And we can also look at that both of these are really used almost exclusively with the context of swallow. Okay, so this is just some basic, there's no machine learning happening here, but these things can be useful to explore like a large text that you don't want to read in detail. You can also do like here, like now I want to look at the inaugural address corpuses, which includes all of the addresses going back to 1789. I don't know how recent they are, but one thing that might be evident in something like this is that language changes, right? So language changes over time. Language was quite different 120 or 130 years ago. So maybe some of the terms are like that have been used frequently back in the 18th century are not used so frequently anymore. And so for inaugural presidential addresses, it would be kind of interesting to see how are these words, citizens, democracy, freedom, duty, America, nation, God, and military used. And we can do that by running like a dispersion plot. And it's kind of interesting, like this is just like a very simple, like here we have all of the inaugural speeches together, so we don't actually like see which president gave that speech at what time, but they are ordered. So we can see that basically as time progressed, these terms appeared with different frequency. And so we see that democracy was a word that it really like only appeared in like more recent times more frequently, whereas duty is something that has kind of like vanished from more recent speeches, and America has kind of like really and the use of America has really increased in more recent speeches, whereas nation is kind of like fairly constant, and the mention of God seems also to be kind of like concentrated at in more recent speeches. Okay, now let's take a look at how can we explore text using statistics. So we'll just start by counting the frequency of different words. Let's take a look at the total number of words, which is called outcomes in NLTK speak in Moby Dick, and the number of unique words, which is called samples in NLTK speak. So if we do that, we can see that we have like 19,300 different words with out of 260,000 words. And so here we see the most frequent words. And the most frequent word here is a comma, followed by a the, followed by a period, followed by of, followed by and, followed by a, followed by to, followed by a semicolon. So what that tells us, well, these words are not all that interesting, right? So they are not probably contain all that much information. And we will see that there is a process called stop word removal, like that we have here, that we want to use to make kind of like to remove these very common words. We can also do things like find all of the words in Moby Dick with more than 15 characters, and I find that kind of fascinating, hermaphroditical or circumnavigations, and so on. So these are the longer words. Okay, so back to stop words. So very frequently, when you want to kind of like create a vector that describes in a particular text, which is something that we will use for sentiment analysis, we really don't want to have like the stop words like the this and was and is and the commas and the semicolons and periods in our data set. And so we want to remove these stop words. And NLTK nicely comes with a stop word corpus for different languages. And so we can look at the stop word corpus for English, and you can see things like I, me, my, myself, we, our, ours, and so on. And then we have all of the do, don't, shouldn't, and so on. And so these words, like depending on our approach, we should remove them, but some of them are actually interesting, right? Because if I say not great, but remove the not from my text, my sentiment analysis might be off, right? So I have to be a little bit careful about like which words I want to remove, especially if they modify some specific words, but we're not gonna be so sophisticated today. We'll just assume that we can remove all of these different stop words here. Okay. This is an exercise that I want you guys to do a little bit later, so we'll skip this for now. So let's look at the stop words. Like, is there a difference between the frequency in which stop words appear in text? We can kind of do something like this. Here I'm just like calculating a fraction of content to stop words, and do this for all of the different texts. And so you could say, which of these texts has the most content, the fewest stop words? And it turns out that text number 8, which is kind of like the personal corpus, if you look back up to the list of the documents, has the most contents with like 82% of words that are not stop words. Okay, we can then also look for collocations. And a collocation is a sequence of words that occur together unusually often. And we can retrieve those using the collocations function. So here we see some, like if we look at Moby Dick, we can see that, or not actually sure this is Moby Dick, this might also be something else. Anyways, It's Colonel Brandon, Sir John, Lady Middleton, Miss Dashwood, everything, 1,000 pounds, dare say, Miss Steele. So we get kind of like a couple of these words that are frequently used together, and we get a better sense of what's going on in the text. Okay, so this was just like some basic stats on text, and now let's take a look at how we can use this kind of stuff to do something with machine learning, and to do some sentiment analysis here. And so like sentiment analysis, as I already mentioned, is kind of like analyzing the sentiment of a particular piece of text. It could be like more nuanced, more complicated. Like, is like a text technical, or but mostly you want to like frequently you want to see, is the text does this have a positive or negative attitude? So for example, if you were to developing the movie critique website Rotten Tomatoes, you might want to like run something like sentiment analysis on the reviews that you integrate in your system, and then designate whether a particular review is fresh or is rotten. Or we have frequently seen this, like this is used by plenty of companies to monitor social media about any mention of their products or of their like company name. Like for example, I do know that Disney looks at sentiment analysis for people that are blogging about the Disney parks. And they really want to understand if somebody says something very negative about them, or also if somebody says something very positive about them. So this is a very common thing to do, and it's kind of like nice because you don't have to like read everything. You can get a sense of something is very negative or very positive, and then you can kind of like selectively take a look at these kinds of problems. So we want to do a sentiment analysis of movie reviews here. And like we will use a corpus of 2,000 movie reviews together where the user sentiment polarity was coded for us. So we have like a classification, is it positive or negative? And you can find more information on this link here. Our goal is to predict the sentiment polarity from just the review. And something we like as a human, we can do this like easily. We have an example like that movie was terrible, clearly a negative review. That movie was great, clearly a positive review. But as we saw in Vivek's lecture, text is not always that unambiguous, and of course movie reviews can also be much more ambiguous. So let's see how good how good of a classifier we can build. But let's first start looking at some of these reviews. So here we have the data set with 1,000 positive and 1,000 negative movie reviews. And you can like look at the path to these individual reviews. They're stored in these files. And we can also just access the positive or negative reviews explicitly. So here are the first ones are the first 1,000 are the negative ones. The second 1,000 are the positive ones. And then we can look at like how many reviews, like what is the what's the distribution of positive and negative reviews, and we can see that we have in fact 1,000 positive and 1,000 negative reviews. So now let's take a look at a particular movie. I'm taking the third movie from this in this list, and this is a negative review for The Mod Squad, which is like a movie from the 90s, and it seems to have a pretty bad review. Anybody seen that movie? It's not like, it's been a while, and it's not probably a movie for the ages. So I'm not surprised if you haven't seen it. But it has kind of a rotten rating on Rotten Tomatoes. Only 3% of all reviewers, 2 out of 63 reviews on Rotten Tomatoes are positive. So we would expect, and the audience also didn't like it, so we would expect it to be like a fairly bad review. So let's take a look at this review. Here is the whole text. I did extract some kind of like interesting sentences here for us to like take a look at. It is movies like these that make a jaded movie viewer thankful for the invention of the Timex Indiglo watch. Well, that's a little bit dated. Sounds like a cool movie, doesn't it not? after the first 15 minutes, it quickly becomes apparent that it is not. So this is kind of a tricky sentence. It's very obvious that it's negative, right? But it has these inversions in there. And so if we do stop word removal, maybe we can't pick this up. Or here we have nothing spectacular, again, an inversion. Avoid this film at all costs. Unfortunately, he's not enough to save this convoluted mess. So that's a very clear statement, right? That this is like a negative movie. And so let's build a custom algorithm to classify the sentiment here. So I'm only going to use methods that we've already seen. There's nothing new here. So what do we do here? We create, like, we are setting up here our labels in a way, like with our Y, as we can ingest them in scikit-learn. And then we can see that we have, in fact, the 0, like the first movie is a -1. The last movie, or the 1000th movie, is the first positive one. And so those are, in fact, correct. We now have labels that we can use. 0 is negative, 1 is positive. Then we can collect all words into a nested array data structure. So here I'm just taking, I create like a long list of all of these words. And you can see here, the first 10 words of the third document is exactly the Mod Squad review that we looked at earlier. And now we get all of the words in the reviews and make a frequency distribution and pick the most common 2000 words. And we also remove the stop words. So here, like, we take the words, we make them all lowercase, and then we use the 2000 most common words. And then we remove the stop words here. And then we remove punctuation marks. So here with the is alphanumerical, so that way we remove all the like semicolons and periods and so on. And then if we look at this, we will get the most frequent words here are film, one, movie, like, even, good, time, story, and so on. So okay, this is kind of like our that we will working with, and then we can extract this word list now from the frequency tuple, and now we have exactly the list that we want. And then we define a function that takes a document and returns a list of zeros and ones, indicating which of these words in word features appears in a document. So like what we do now is we take a review and look at this list, and if the review contains the word film, we give it a 1. If the word contains the review 1, we give it a 1. If the word if the review doesn't contain the word movie, we give it a 0, and so on. And so now we're creating this binary vector for each review based on these selected words, the most frequently used words here. So we have like our feature vector created like this. And this is exactly what I'm doing here. Now, if we do that for the third movie, we can see here is like our data set. We have the 1, 1, 1, and then some zeros, and so on. And then we do this for not only this particular review, but we do this for all of the movies. And now we have like our actual data set that we want to use. Like this is kind of like now our kind of like data that we want to use to train a classifier. And now we have X and we have Y, we have our data and we have our labels, and then suddenly we have a classification problem, right? So we can just apply standard machine learning to this. And NLTK does have a built-in classifier, but I first want to stick with the built-in scikit-learn classifiers to make sure that everybody is very crystal clear on this, that there is no magic to this. This is exactly the same stuff that we've done before. So if we were to run k-nearest neighbor classification with a k of 30 and do some cross-validation, we like 10-fold cross-validation, we can see that we get some kind of like accuracy scores between 0.5 and 0.7 maybe. So that's not all that great, right? So like if you just had a guess, you would have 50% accuracy. We can try if SVM does better, and as usual, SVM takes a little bit to run. But what we will see is that for these parameters and for this configuration, that SVM will actually perform much better than our k-nearest neighbor classification here. We'll see that the accuracy scores are in kind of like the 80% range. Of course, we haven't done anything like cross-validation to pick parameters. So we could use cross-validation to find optimal parameters for K and C. But of course, this is kind of like, as you probably know from the homework, that SVM, especially, it takes a while to run. Okay, still waiting. I guess I shouldn't have cleared the notebook here, but it should not take too long. Okay, here we go. We have somewhere between like 78 and 83, like sometimes we go even 86. There's a question, is there a reason why you chose a gamma value of auto versus scale? Just a little bit of experimentation, so I don't have like empirical reasons for that here. Okay, so let's see what our algorithm thinks of the mod squad. I'm gonna like now like here I've just calculated the scores. I'm gonna train like a classifier now and do a trained test split, and then now I am kind of like looking at the mod squad, and I am like predicting the mod squad, and it gives us like a negative. It gives us a negative review classification. So we have successfully built a classifier that can detect that this particular mod squad review was a bad review. But yeah, we do expect that we have somewhere between like 22 to 15% of misclassifications. And so it would be interesting to see what is a misclassified movie. So the first 1,000 movies are negative reviews. So we can just look at the first one that we classified as positive. And this is kind of the 9th one here, index 8, which is movie Aberdeen. And if we look at Aberdeen on Rotten Tomatoes, we can see that it has like overall, it got like a fairly positive sentiment, but one particular review that we were trying to classify was negative. And so maybe let's take a look at what is going on with that review. And we can see, like again, here's the whole review. I pulled out some interesting highlights here. Like if signs and wonders sometimes feel overloaded with ideas, at least it's willing to stretch beyond what we've come to expect from traditional drama. Yet this ever-reliable Swedish actor adds depth and significance to the otherwise plodding and forgettable Aberdeen, a sentimental and painfully mundane European drama. So clearly, this is not a great review, but it's also not a terrible review. So this is kind of like a borderline case. And so maybe it's forgivable that our classifier made a mistake. Maybe if we had some kind of like scores, we could use regression instead of like hard classification. Like, is it a very positive sentiment? Is it a very negative sentiment? That would be also interesting to see. Okay, any questions about this approach before I kind of show how you can do this with NLTK built-in tools? If not, let's just take a look at how you can do this with NLTK. This is like more or less based on this chapter from the NLTK book. I am kind of like here just retrieving a list that contains top tuples where we have reviews stored as an array of words as the first item, and then the category is the second. We can then extract the features from all of the documents as we did before. And here is kind of like, if a movie contains film, then true. If it contains one, then true, and so on. So here we have kind of like the our features. And then we can do similar as we did before. We split it into a training set, test set, and then we use NLTK's built-in naive Bayes classifier. and train that classifier on our training set, and then we run that on we run that on our test set, and we get like an accuracy of 88%. So we can see that this particular way of doing this, they had a little bit of a better approach of picking the words, and like maybe a better classifier for this particular problem. We can see that we can actually get a fairly good accuracy score of like 0.88, which is great. But even our homemade and very naive algorithm, where we didn't take care of any inversions or anything like that, achieved a respectable 80% accuracy. So obviously, we could have used more data. We could have used in our homegrown model words that discriminate between good and bad reviews instead of just like the most frequent words. We could have used Ngram to catch the not bad as a positive sentiment, and so on. So there's many ways that we could have improved this. But as you can see, like even like these basic approaches for something as simple as binary sentiment classification are pretty good and pretty reliable. Okay, so that wraps up the NLP part. And now I'll do like a quick 5-minute break. We'll return at 1:02, and then we'll jump right into regular expressions. Okay, so now let's talk about regular expressions. Regular expressions are a way to match strings based on some logical rule. They're actually more or less like a mini programming language for doing exactly that. Regular expressions, there's different flavors, but they are all very similar. So if you know regular expressions in Python, you can use them in JavaScript or in any other programming language. They are kind of like hard to read and easy to forget exactly. But my goal for this here is to kind of give you a bit of an idea of what are the possibilities and to understand the different rules. And then if you actually need to use the regular expression, you'll probably have to like look up exactly the different conventions and play around with it. So nobody really can write regular expressions just from their mind. It's always a little bit of a trial and error, and it's always like much easier to write than it is actually to read. What you can do with regular expression, you can try to kind of like extract some kind of like structured information from text. So like when we talked about web scraping, we were able to extract the URLs based on the beautiful soup functions, but there would be different ways I could get the href attribute with a regular expression if I had, for example, like one big text file with HTML text. Or I could go to people's websites and try to find whether they have posted their email address with some kind of like, or maybe even with some kind of obvious obfuscation, and extract these email addresses and then send them spam email, which is, of course, what regularly happens if you put your email on a website. So the basic syntax to, like, in Python, we have this RE module, which isn't this is kind of like core Python. And the basic syntax to search for a match in a string is this. Here we have our RE library.search. And then you put in your regular expression pattern, and then you put in like what you want to search in. So pattern is the regular expression, text is the text that the regular expression is applied to. And then match holds the search result that matches the string in an object. Like we had when we were looking at web scraping, we have either find only the first instance with search or find all of the instances with find all. Sometimes it's also useful to split based on a regular expression. So I'll use search to demonstrate and find all to demonstrate, but sometimes I also will use split to demonstrate. For example, if I want to split based on a comma, I can use the split function here. So here's our first very simple regular expression. We have the actual literal word, animal, and then then these three like W's that like \w, \w, \w. And this is supposed to match the substring animal followed by a 3-letter word. And the 3-letter word, we have encoded it by these like \W's. And so \W means any word character. And so let's take a look at this. So here we have an example text, an example animal cat, exclamation mark, animal dog, exclamation mark, and animal hedgehog. And now we can run the search on this. And if we do that, we can see that we have actually found animal cat. So one little detail here is that I'm using a raw string. We've seen like different types of string before. The benefit of using the raw string here is that I don't have to escape the backslash. So if you're using raw strings, it is a little bit easier to write regular expressions. Like if I didn't use a raw string, I could write this expression like this. Then I would have to always escape this backslash, which is a little bit more annoying. And then we can actually retrieve what the exact match is by calling match.group. The reason why we have to do this, I'll explain this a little bit later, but just like as a preview, like we can do like nested matches, and then we get different groups of matches, and that's kind of like just the default way. So you have to call .group to retrieve the particular instance. So here we have found our animal cat, and notice that I didn't include the exclamation marks here. Okay, so that was just like the first example. Now let's look at this a little bit more formally. First, we have like ordinary characters such as like like an X or a 9 or smaller than. They match themselves literally. So I can do something like search for a regular expression SC in the string data science, and we can see that this actually retrieves SC. So not particularly exciting, but okay, of course, we now know that the string actually exists in that element. We can also search for the occurrence of a smaller than sign, and that works just as well. However, there are special characters in the regular expressions, and we have these like dot, hat, dollar, star, plus, question mark, and various brackets and pipes and slashes and so on that have special meaning. And so if I wanted to use any of those, like here, like the hat symbol searches for the beginning of a string, not the actual hat symbol. So if I were to do this, I just get like a pointer to the beginning of the string, which isn't particularly useful here, but can be more useful in a more complicated expression. If I wanted to search for the hat, I have to escape this special character with a backslash. And so if I do this, I can actually find that particular. Okay, now, like, what is the meaning of some of these special characters? Like, of course, this isn't particularly interesting, right? Just looking for SC. What we want to do is we want to use some kind of wildcards and develop some rules of what we want to match. So here, like a period is the first one, is that matches a single character, but not a new line character. So if we say like a regular expression was just a dot, and then we should be able to, like, we are not actually matching the dot here, right? But we are matching the first single character. Can everybody hear me? I just got a message from my Zoom that my connection is unstable. Okay, looks good. Similar to the dot, we already used this, and the backslash W lowercase matches a word character. And the word character are letters or digits or underbars. So like we have A to Z uppercase, and then 0 to 9 and the underscore. And it only matches a single word char, not a whole word. So if we do this here, like search for a word char in data science, we get the first response here. And if we had this input string here, like the smaller than sign here is not actually a word char, so we will still get our D. And inversely from our word char, the uppercase W matches any non-word character. So if we were to do this on the same string here, we would actually get the smaller than sign. S matches a single white space character, either a space, a new line, a return, a tab, but there's also other white space character. So that is useful, for example, if I want to split a string by white space. So if I have this string here, intro data science, and then I'm running split on it, then I get like an array back where I've split those two words. Inversely, uppercase S matches any non-white space character. So if I were to search for the first non-white space character, like I wouldn't get this space back, but I would get this I back here. T, N, and R match tab, new line, and return respectively. So if I have kind of like this string here that is kind of like printed with this like tab character here, and then here I have individual spaces. If I were to split this, I can see that this actually successfully split by the tab character. D matches decimal digits from 0 to 9. So if I were to like search for this, I would retrieve my first decimal digit that I am encountering in the string. Also, I mentioned this already, that hat matches the start of the string, dollar matches the end of the string, and that these are useful for larger regular expression, but not particularly in isolation. Okay, so we've now been able to pick individual characters or exactly specify what we want to match. But now we want to get a little bit more general. And to do that, we have to use repetition qualifiers. For example, like the first one here is a plus sign. And the way this works is I take some kind of expression like here an O, or it could be like a word character or anything like that. And then I tell the regular expression how often I expect this. And by saying O plus, I want matches one or more occurrences of the pattern to its left. So if I have this intro data science, what I will match is all of these O's. Star matches 0 or more occurrences of the pattern on its left. So for like what I'm doing here is I'm searching for digits possibly separated by one or more white spaces. So here I have like D, S star, D, S star, D. And then I have the string XX1 space 2 space 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 3 XX. And if I now run a search on this, I get my like 1, 2, 3 extracted out of it. This also, of course, works if there are no white spaces. Exactly same regular expression, because the star indicates that S might be optional. We can use this, for example, to look for words starting with a certain character. So if we wanted to say D slash word character star, we would want to get all of the like words that, or like the first word in this case, because we're using search, not find all. We would get the first word that starts with a D. And so here now we have extracted data science. Analogous to the star and the plus sign is the question mark, but the question mark matches 0 or 1 occurrences of the pattern to its left. So if we do this here, we get the result DA. I'm saying 0 or 1, and I am actually getting 2. Like I'm matching the A here, but I could also match none, right? Because it's 0 or 1. And so the reason for that is because by default, all regular expression qualifiers are greedy, so they try to match as much as possible. I can explicitly turn that off. I'll talk more about this a little bit later. Just be aware that the 0 or more condition can be tricky. For example, if you wanted to match a DD with a star and were to do it like this, we get a 0 match because the start of the string already matches the or 0 condition. So if you wanted to use this, if you wanted to do this, you would have to use like a D plus here. So now let's take a look at using this in something that is reasonably interesting. Here I have like a piece of HTML, and I can say you can reach me at href, and then the syntax for specifying a mail address, mail to alex@sci.utah.edu by email address if necessary. So okay, how can we do this? We want to match word characters, then an @ and then more word characters. There are also some dots in there. But let's just try this with word characters. Let's try with word, at least 1, but maybe more, then an @ then word characters again, at least 1, maybe more. And then if we retrieve that, we get like a partial result. We get alex@sci. So clearly, we have that the word character wasn't the perfect choice here. We have to do something a little bit more complicated. So we could say, well, let's look at this sci.utah.edu. We could say, I want this part here is the same now. And then we do word character, at least 1, then a dot, because I'm escaping it here. Then a word character, then a dot, and so on. And so if I do that, that would work. But it's not very general, right? Because this works for this particular format of an address where I have like this subdomain.sci.utah.edu, but it doesn't work for all possible legal email addresses. So if I had an email address like this, alex@utah.edu, this would actually not work because that is just like a too specific regular expression. So could also, like, this would also fail for a case like this where alex-lex@sci.utah.edu. And so if I use the same thing as above, this just gives me like a valid, well, an email, something that looks like an email address, but it's actually not the correct email address. So I have to do something a little bit different. I have to like come up with a better solution. Just pure word characters isn't going to work. And so to fix this, we need another concept. We need to explicitly specify the set of legal characters. And we can do that by using square brackets. When we have square brackets enclosing an expression, then all of the characters within that expression match. So it basically says any of the elements inside the square brackets are supposed to be matching. And so here I have square brackets, words, word characters, or dots, or dashes. And I want at least one of them, but as many as you can find, then an @ sign, and then the same thing, word characters, or dots, or dashes. And so this now successfully extracts all legal email addresses. It does work for, like, as you can see, for this email address. It works for the other one. It also works for like the, what is it, HTML2. It also works for this one. So it works for all of these different examples. So this is great. It was like super easy to write this regular expression from note that we didn't escape the dot here. And that's something special about inside the square brackets. Inside the square brackets, you have only to, you only need to escape these characters, but you don't need to escape like the dot, the hat, and the dollar. They are treated as literals inside the square brackets. So one thing is that this pattern matches all valid email addresses, but it also matches other stuff that is not a valid email address. So this is like a regular expression that you could use to extract email addresses from a website, but it's not a regular expression that you could use to validate an email address, let's say, in a web form. So for example, this here would be not a legal email address, obviously, because there are 3 dots, but it would actually match the regular expression. So I would have to write a different regular expression that takes care of something like this. Okay, any questions so far? Okay, so one thing that I can do if I want to be more specific about repeating substrings, I can use grouping. And we can use grouping with round brackets. And so here I am like saying DA is exactly the substring, and I want to have 1+ matches of the string. So if I were to do this, I get this DA extracted from that here. But groups can also be very handy to match a larger string, but only extract a part that is nested within the group. And that's why we have all like these group calls here. So the group method we've been using provides access to all of the match groups independently. So for example, if we had a URL in a website like this here, we have like href equals and then our URL in quotation marks. And what we could do is we could use the href here to identify the links, but then, and then like here we have the quotation marks, but then use what we really want is only the content of between the quotation marks, but not the rest of it. And so because we really only want that part, we just put it in round brackets into a group. And here is like a regular expression that matches a URL. I start off with like a word character and then a colon, and then a slash, and then other characters. And what I get here is that if I just call from match.group, I get the whole match here. But I also can extract only the match within a particular group that I have denoted by my round brackets here. So if I run match.group, give me the first one, the explicit group, the group at index 1, I actually get that URL out. So that can be handy if I have a complex expression that I use to match something, but what I really want is only a sub part of it. I can also use groups just for logic. That is also absolutely okay. And now, so far I've always used search or split. And now let's take a look at find all. So here is like a little bit of an HTML snippet where I have two email addresses, mine and Anna's, and I can run this regular expression on them, and I get back an array of all of the email addresses that were found in that particular text. And then you can also combine the find all with groups. So here I am I'm creating a group for everything before the @ and the group for everything after the @ and if I do that, I have now extracted like Alex Lex and the domain separately, and similar little and the domain separately. You can see this is in a tuple, which is what the group returns, so I could access them individually. But if I wanted to do this just for logic and not for the purpose of grouping, I can use this special syntax here, which has this question mark colon syntax that tells it it's a non-capturing grouping. So in this case, I only want to use it for logic, and that way I could use these round brackets that way, and it would just extract the whole email addresses. Okay, so I mentioned earlier that regular expressions by default are greedy, which is often good, but not always. So here, if I have this HTML text here, and I wanted to extract the B tag or any tag, right? I wanted to answer the question like which tags are being used in this particular HTML. And the way, if I were to try this with I have my opening, my opening tag symbol, my closing tag symbol. In between, I have characters, like at least one, but multiple. I have multiple characters basically. If I were to do this, what I get, because it's a greedy match, I get like just this one big thing, because all of this stuff here matches between this opening and the closing tags. And so clearly here I want a non-greedy version. We can modify this behavior to make it non-greedy by adding the question mark character, which signals that the expression on the left should not be greedy. So here, if I just add this question mark, then I'm telling it this expression here, that should not be greedy. And if I do that, I get actually the tags that I wanted to extract. And this modifier, like greedy or not greedy, applies to the star, the plus, and the question mark operators. And this is, of course, a little bit weird because the question mark now has two different meanings depending on the context. So it means either at least one a character, one or more characters. So I could have all of these are different, are legal sequences, which is something like in this case here, the first question mark has a completely different meaning than the second question mark. It's just something that you have to be aware of. Okay, I can then also specify character subsets with dashes. So for example, I can do things like, say I want digits 2 to 9, and that kind of assumes the logical ordering. So that includes digits 2 and 9. If I do this on the string, I extract all of these 2, 3, 4, because 0 here isn't included. When we can also combine this with character set, and we can use this hat operator, again, another example of an operator that is used for different things. We can use this to invert the match. So here, this tells me all of the symbols except for 0 to 2. And so if I do that, I get a match 3, 4 here. And then finally, I can specify explicit number of copies. So for example, if I wanted to extract area codes in brackets, we have these are 3 digits. And so I wanted to extract these area codes, but I don't want to extract these here. I can do that with this regular expression here. I'm escaping my parentheses, then I'm using the parentheses to group here. I'm saying 0 to 9 exactly 3 times and extract it from a phone number, from the phone number's text, and I get these area codes here. I can also give ranges. So here I use just 3, but I can also say 2 or 3, or 2 to 3, which would give me like the result, because I have this 12 here. So this matches this one here, but it doesn't match this one here. Then the final operation that I want to introduce is the OR expression. So we can use the pipe operator to define any an OR between any regular expression terms. So I could say, like, I have a text like, we could meet Monday or Wednesday, and then I can write this regular expression Monday or Tuesday or Wednesday or Friday, and so on. So this would match any of the weekdays. I can see here, like, I have my Monday and my Wednesday that I actually found in this particular string here. And then I could also, like, well, I could apply this in a different way other than just for finding something by using the, by replacing strings. I can substitute something. For example, I could say Monday, Tuesday, Wednesday, Thursday, Friday. I want to replace all of them with the weekday string. And in this particular text, and then I would have, we could meet weekday or weekday. Okay, so I'm sure this was a lot, but I hope that you get an overview of what kinds of regular expression there are. And here's just some other pointers that you could maybe use. But now I want to kind of like answer any questions you might have, and then start like a breakout rooms for our exercises. So questions? Okay, well, if not, here is the exercise. The exercise has a little bit of NLP in here, but much of it is regular expressions, and just like applying what you just saw. I'll set up the rooms. Let's see. Okay, well, thanks everybody, and the rooms are going up now.